Okay, awesome. Hello, everyone. Welcome back to Advanced Track. This week, we are going to be going over uh, word embeddings and recurrent neural networks. In the past few workshops, we've been looking at convolutional neural networks. We discussed how, that's one kind of neural network architecture and model that's suited for completing specific kinds of problems and whatnot. So now we're going to be looking at RNNs, which is a different type of model suited for its own kind of problem spaces. So yeah, as always, the slides are on the screen right now for you guys. And the attendance code this week is Mango if you want to get your points. So yeah, also please remember guys to have your Conda environments set up by next week. So if you guys remember, um, can either Ben or Justin get the link to that doc that was hyperlinked in the chat for everyone? So there was that doc that we linked to you guys a few workshops ago in the
Yeah,
slides.
there should be an
Um,
explanation too, or what to do with the dock and how to set it up on one of the later slides. But I'll also add the link
yeah.
right now.
So just please have that ready by next week. And if you don't, I think we're going to be hosting another office hours on this Thursday, if I'm not mistaken. So you can ask questions about any problems you might be having there, and also just like towards the end of this workshop, like at the end, you if you're having problems, just like let us know. It's important that you have this set up by the next workshop because next week we're going to be doing PyTorch, and it's really helpful that for you guys to be able to follow along with the slides and kind of what's happening so you can actually start coding stuff. So yeah, without further ado, let's get started. So yeah, today's content. So we're going to start with word embeddings and we'll explain what these are and why they're useful. And then we'll talk about the RNN model architecture and what it's used for and how it works. So yeah, let's start with word embeddings first. So yeah, let's first take a second to answer these questions that will probably seem pretty like obvious to to a human, right? But the point of this exercise is for you guys to kind of explore maybe the kinds of things a machine would have to think about when it's trying to solve some natural language processing task. So, yeah. So this we have two sentences here. So the baseball player ran over to catch blank, and the grizzly bear goes over to the river to catch blank. So let's just lightning round again right off the bat. Just like unmute and like tell me, guy. You guys can tell us what you guys think some logical answers for this first sentence are, and then how you knew, how you made that prediction, and then yeah. So go ahead.
First one, the ball.
Yeah.
I'm guessing because of baseball player.
Cool, cool. So yeah, we have this kind of context clue um in the sentence that says baseball player, right? So what's it, and the kind of thing that's important to realize when we're looking at this is that the word baseball and this word are probably related to each other in some way, right? And so and that's probably what your mind is implicitly doing when you read the sentence and then you predict what it is, right? You're saying you kind of implicitly develop some connection between the words that we have and what this word that we are missing should be. So that's an important theme to keep in mind. Does someone else want to uh, take a shot at the second sentence?
Uh, the grizzly bear goes to the river to catch fish.
Yeah, perfect. So, why do you say fish?
Well, it uses the verb catch, so it's like that's usually you can catch a fish, and then it's at the river, so it's associated with like the river, and usually grizzly bears eat fish.
Yeah, right. So that's perfect. So we there's a lot of information that we can kind of extract from what we already have in order to predict this, right? So for one, we know grizzly bears commonly eat fish. Two, we see that there's a river involved in this sentence. So that kind of further enforces the fact that, okay, maybe we're looking at fish. And then on top of that, the grizzly bear is catching something. So that's a third reason, right? So there's all these context clues as to why you would maybe say fish here, right? So it's important. Obviously, like when you guys look at these sentences, you probably immediately think of an answer just as because we're all humans. But it's important to kind of take a step back and analyze, okay, what did my brain do to get that prediction? Because that's very important to understand that explicitly, because the machine has to kind of go through some explicit steps. It's a program, right? It has to go through some explicit steps, form some sorts of relations in order to make predictions, right? So we have to actually analyze these reasons. Okay, so what are word embeddings? Okay, so computers don't like words, right? We can't just talk to computers, right? So most of you guys are probably, CS majors, maybe some of you aren't, but like I'm sure everyone's heard at some point, the language of the computer is like numbers, right? So it works in like at the lowest level, like ones and zeros, right? So ultimately, the computer needs to work with numbers. So if we look at all the examples we've seen in the past, for the past couple of weeks, right? So the first few weeks when we were looking at the fully connected network, our input was sort of those 784 pixel image values for the handwritten digits. And then when we looked at the CNNs, we kind of had that volume of pixels for the 3 color depths, right? And in all of those cases, all those things are clearly modeled by just like a sequence of numbers, right? So in every case, all of those numbers commonly will be like a number between like 0 and 255. It doesn't have to be, but it's some number, right? So we can't just give the computer words, right? It won't understand what we're saying. We can't just like talk to it. So kind of the task here for the computer is what we just discussed, right? So like you can imagine the inputs here would be like these words, right? That we already know. And then given these words, we kind of have to predict this what the last word in the sentence is. So this is kind of these first words in the sentence would kind of be our input, and then the network's output would be its guess for what this word is, right? So let's discuss for a second, like kind of how would we just get some ideas on how we could like represent words as like in numerical representations. I don't expect you guys to like get this like right off the bat, but just like some intuition for like, okay, what kinds of things could we do? The answer is kind of laced in like linear algebra and whatnot. So
I imagine we could break a sentence into a subject and predicate.
yeah, so that's one thing we could do. That's a good point. So you could kind of provide explicit labels to the machine, explicit features, saying like you could give it one group of words that are like subjects, one group of words that are like predicates, like you said. So that's one option. That's completely valid. It's a great answer. It's not the one I was looking for, because I'm just kind of saying like, how can we turn like a 4-letter word like potato? Well, potato's not 4 letters, but how can we turn a word like potato into a bunch of numbers? So if you guys have taken like linear algebra, maybe you can kind of
Maybe
think
a
of
vector with
okay.
one representing the letter.
Okay, so
it would
yeah,
be
go ahead.
like a bunch of ones and zeros, and then like for example, P, like in the alphabet, the number corresponding to P would be the 1.
Yeah. So I think what you're saying is basically each word is like a 26 element vector, one for each letter, and then if the corresponding slot is like a 1, then it's like, okay, it has that letter, and if it's a 0, it doesn't have that letter. So that's a decent idea. The problem is like that has no ordering, right? How would you order because there's a lot of words that like have the same letters in them, but those letters don't come in the same order. Or what if the word has more than one letter in it? or more than one of the same letter in it. But that
Oh,
is
I meant
Yeah,
like
what's
for
up?
each letter a vector. But I would think that would be computationally inefficient. But
Yeah,
Yeah.
but this is okay. This is kind of on the right track. So I like that. I like that kind of thinking, because initially what happens is we do start with. So we can move on here. Initially, we do start with something that's kind of inefficient, and then we can kind of make that something a lot more efficient. So yeah, basically so you guys were right. Like we need to basically encode these things as vectors, right? So we need some sort of numerical encoding, and that will be in the form of a vector. So each word will have some unique vector that basically corresponds to that word. Okay, so the question is, how is this vector represented? How do we come up with these vectors and whatnot, right? So before we get to that, first we have to define something called our vocabulary space. So when we do natural language processing, um, there's a lot of words in whatever language we're dealing with. So let's just say we're dealing with English for now, right? There's so many words in the English language, right? So if we wanted to kind of have all of the words in the English language, like and we wanted to find a vector that represents each of them, that would be ridiculous, right? Like you guys can imagine, just from a computational perspective, it would be very hard for us to create a unique vector for every single word in the English language. So what commonly happens is we'll go ahead and in sort of smaller scale applications, like kind of what we're looking at, we would go ahead and look at the kind of data we have. So let's say your data is like some Harry Potter book, right? So you have some Harry Potter book, and that's like your data set, right? What you could do is you could go through that Harry Potter book and then grab the 3,000 most commonly occurring words, right? And then that would make up what's called our vocabulary space. So instead of grabbing every single unique word that's in the Harry Potter book, we would choose kind of the 3,000 most commonly appearing ones. And there's a bunch of interesting videos that kind of explore the depths of linguistics and whatnot. That kind of explain what I'm about to say. But basically, if you do that, you'll basically catch like 99% of the words that are going to show up in that Harry Potter book. You'll miss a few of them, obviously, but you're going to get almost all of them. So we grab like those 3,000 words, for example, and then now our vocabulary space is restricted to that. So then we just have to find vectors for those 3,000 words. Okay. So that kind of makes our problem space and our task like a lot more manageable than it would have been otherwise, right? So how are we going to go about doing that? So the most common method or kind of system / model that natural language processing researchers use right now to generate word embeddings is this model called word to vec. So word to vector, right? That's what it means. So and by the way, in case it wasn't clear, so when we say word embeddings, so the embeddings just refer to those vectors of vector representations. Those are the embeddings for the words. So yeah, now we've restricted our space to some vocabulary that's, let's say, 3,000 words. It can be any number of words, but let's just say it's 3,000. And now we're going to use this thing called word to vec to create vectors. Okay. So how do we kind of start? So this is the way we start is kind of like, in a way, like similar to some of the things you guys brought up as we were discussing earlier. So at first, what we do is for our 3,000 words, we develop 3,000 vectors. Okay. And then for each of those, we develop 3,000 vectors, and each of them have 3,000 elements in them. Okay. So imagine 3,000 separate vectors, and each of them have 3,000 elements. Okay. And then in each vector, everything in the vector is 0 except for the corresponding word. So you can imagine if we just look at one vector, okay, in our vocabulary space. So if our vocabulary space is 3,000 here for this vector at the top, that would mean, like, in this example, like Rome would refer to the first element in the vector, Paris would be the second element, etc. Like potato could be the third one, cheesecake, strawberry, whatever, right? So then each kind of element corresponds to one word in the vector, and then whichever one is like lit up with a 1, with a value of 1, is what the word is. Okay, so I'm going to stop for a second and make sure that's clear to everyone. So basically there would be 3,000 unique vectors, right? Because if you have 3,000 vectors and you light up one different value, and there's 3,000 different values in each vector, then each vector would be unique. Can I get a yes or no if that kind of makes sense to people? Just like in the chat will do. Okay. Okay, so it seems like that makes sense to everyone. If it doesn't make sense, just like let me know at any point. So yeah, this is a very common theme in machine learning, and it's called one-hot encoded vectors. So one-hot encoded vectors, as the name implies, is like, so one hot. So you can imagine all the zeros are like cold, and then the one is like hot. So it's like one hot encoded means basically one value is lit up with a one, everything else is a zero. Okay, so this is cool. We have some sort of way of representing all of these words, but this is still kind of useless. And yeah, so I was gonna see if you guys, I don't know, does anyone kind of have an idea of why this isn't very helpful? The answer is not extremely obvious, but there's kind of two reasons why this is not very helpful. One of them is like kind of obvious, and the other is like not as obvious. So go ahead.
For one, it seems computationally inefficient.
Yeah, so that's kind of the more obvious one, right? So this is still kind of like pretty inefficient, right? Like we have like very large 3,000 vectors that are each like 3,000 elements. That's like a lot of memory that we're just holding vectors. And you can imagine this is not very efficient, right? Because like the data is just not very dense, right? A big theme we've been talking about in machine learning this whole time is kind of we want to extract very dense and information rich vectors from like our initial space, right? So when we talked about CNNs, we recall that we kind of started with some not very dense information, right? The information was just like pixel RGB color values, right? But then as we pass through these convolutional layers and whatnot, what that kind of does is identify higher level features after each layer gets higher level features until the kinds of things that our vectors are representing after a while are just like actual patterns or very rich information, right? And that's kind of what makes it easy at the end of the day for that CNN, when we just pass it into those few fully connected layers at the end, for it to kind of give us an accurate prediction, because we're feeding it really dense information. So here, we're not feeding it very dense information, right? It's very sparse. It's like almost all zeros, just one and one. So that's kind of a big reason why this is not super helpful. There's also another reason why this is not helpful. So the idea that we need to look at, so this is kind of laced in linear algebra, as I was saying earlier. So if you guys have taken linear algebra, you'll kind of know that if you take the dot product of two vectors and that output is 0, right? That means the vectors are orthogonal to each other, right? So that means they're at like 90-degree angles to each other. And what this kind of relationally or conceptually means in this context is that the words don't have any relationships with each other. They're kind of, so they're all in some vector space, kind of like you're looking at in this image here. But because they're all orthogonal to each other, they're all at 90-degree angles to each other, we can't really derive any relationships between those words. So for example, like the word like food and like baguette, right, should be somewhat related to each other in some ways, because baguette is a type of food, right? But if all of the vectors are orthogonal to each other, that means none of the words have any relationship with each other. So the relationship between the word baguette and food is just the same as the relationship between the word baguette and like, I don't know, like mountain, right? It's two words that like actually don't really have any relationship with each other. And this is problematic, right? Because if we go back a few slides, remember we discussed how did you kind of come up with the answer to this question? And what we kind of deduced is, well, we kind of noticed that there's relationships between the word baseball and like the ball here, or there's a relationship between grizzly and catch and river to like fish in this context, right? Those words have some sorts of relationships to each other. And that's the only way that we really got the answer at the end of the day. So if to the computer, right? Because to the computer, all we're giving it is numbers, right? So if we just give it these one hot encoded vectors, the computer can't see any of those relationships that we use to get this prediction. Okay. So I think that's a pretty intuitive way of kind of understanding why maybe this isn't extremely useful. So does that kind of make sense to you guys? Do you kind of understand what the problem with these one hot encoded vectors are? Can I get a yes or no or thumbs up or whatever? Okay. Cool. Yeah. Please like do not be afraid to ask questions. Like some of this is like confusing and we understand that it's confusing. So if you don't get it, just like throw a question in the chat. Okay. So what we need to do is we need to, instead of just using these one hot encoded vectors, we need to develop something that such that each vector, each word in our vector space is related to each other in some way. So you can imagine basically like what we kind of want is, if you're looking at this kind of visual here of this vector space, the word like baguette and food should not be like completely orthogonal to each other. They should maybe be like, the angle between them should be like pretty small, right? So the angle, if the angle between them is like 1 degree instead of like 90 degrees, that means like those words are like pretty related. Okay. Because when you take the dot product of them, if you get a large value, that means those words are kind of related to each other in a way. Whereas if you take the dot product and you get 0, right, as we discussed, that means like there's no relationship between the words. So we want it such that all of the words that are similar to each other are kind of have small angles between them in the vector space. So they have kind of similar numerical representations, and all the very different words have very different numerical representations. That's kind of the goal when we make these word embeddings. So how do we do this? So word to vec is how we do this. Okay. So the way word to vec works is it just uses a simple, fully connected neural network. So that kind of architecture that we talked about in the first 2 weeks, where every neuron is connected to every neuron in the next layer, and so on and so forth until we get to the output. Okay. So the idea here is that we pass these one hot encoded vectors into this word to vec model. Okay. And then the output should be a prediction for a word. And then the word embeddings that we're actually going to end up taking are the weights that we learned. Okay. So that probably didn't make a ton of sense. So we're going to go through that step by step. Okay. So there's kind of two models of how word to vec works. So there's one called continuous bag of words, and then there's another one called skipgram. And there's different reasons for using each of them. And you'll kind of see that they're kind of opposite to each other. And there's some context in which one is better than the other. We're not really going to get into that. We're just going to kind of go over word to vec in general. Okay. So this is kind of on the right side. We kind of see a visualization of the continuous bag of words word to vec model. Okay. So if you guys recall, in our original example, we had kind of the grizzly bear, or that sentence or whatever, and then we wanted to catch a fish, right? So we wanted to predict that the word fish belonged to the end of the sentence. So this is kind of the idea that we use in the continuous bag of words. So what we do is we pass in the input would be a bunch of one hot encoded vectors, and the amount of one hot encoded vectors in this case would depend on the length of the sentence, right? So I think it was like 5 words or something before the fish part, something like that, right? So those words would each be an input into our CBOW model. And then this is just a hidden layer here, this summation thing. And then it gives us some output. And that output is the prediction. So in this case, fish. Okay. So yeah. So in this case, we pass the grizzly bear goes to the river too. So each of those would be an input. And then those are all one hot encoded vectors. And then CBOW will output a single word that's saying fish. Now, there's something very important to keep in mind here, is that this CBOW model is not the model that we're actually going to be using to predict the word at the end. Remember what the purpose of CBOW is. CBOW and word to vec, they exist to generate word embeddings. And then we use those word embeddings in our actual neural network in order to actually produce the predictions. Okay, so this is kind of all like a before step. Everything we've discussed so far is like a before step. It's kind of like, how do we pre-train and how do we so how do we pre-train this data in order to give our computer something that it understands and can make meaningful predictions out of. So don't get this confused with us actually predicting the word fish, because in this case we already know that the output is supposed to be fish, right? So if it gets it wrong, we're just doing supervised learning like we've always been doing, where you compare the output that it gives you to the value of the cost function, and then you do backpropagation, blah blah blah, the same way that it's always worked, right? So the purpose of this is to generate the embeddings. Okay, so yeah, so that's how we do this feed forward backpropagation thing that we've been discussing for weeks. And then what you end up getting here is there's actually only a single, so this is only a single layer, single hidden layer actually in the word to vec model. And then the weights that you get here in your hidden layer are what we use to kind of make the word embeddings. So you kind of take the one hot encoded vector and then you multiply it by whatever the word embedding, whatever the weight value is in the hidden layer, and then that gives you your word embedding. Okay. So that was CBOW, so continuous bag of words. And then there's also skipgram. So skipgram is the opposite. And it seems like a lot harder, right? It's a lot more punishing intuitively, because you're giving the network a lot less information and you're expecting it to make a lot of predictions. So I guess let me explain what skipgram is, right? So instead of giving all of the words in the sentence and then trying to predict the output, here we just give the fish. So here we would just input fish, and then the model has to predict all of the other words that came before fish. So it's kind of the opposite. Okay. So this might seem like counterintuitive to do it this way. So they both work pretty well in terms of generating the word embeddings. Skipgram is generally preferred in some applications, and CBOW is generally preferred in other applications. So honestly, like, I think most people use CBOW, and it's intuitively CBOW is kind of is more intuitively friendly, right? Like we pass in kind of all of those input words and we're getting this output prediction. But there's also skipgram. The only difference is you pass the fish in and you're trying to predict all the outputs. The objective is still the same thing. The objective is to kind of learn this projection here. This projection, so this projection just refers to that hidden layer, right? Because what we're actually doing is projecting the one hot encoded vectors into a vector space such that all the similar words are kind of have small degrees. Okay, so I see some questions. Is skipgram used to avoid overfitting in large data sets? Actually, yeah, I think that is one application where skipgram is more commonly used. I'm not 100% sure. I'm pretty rusty on this, but I think if you have like a very large vocabulary, like one of them's better, and then if you have a very small vocabulary, one of them's better. So I think if you have a large vocabulary, skipgram is good. If you have a smaller vocabulary, I think CBOW is better. It might be the other way around, though. I'm not sure. Does CBOW output the embeddings for each word, or does it output fish? It outputs fish, right? So this is important. So CBOW is trying to output this word, right? But what we actually care about is not that it's outputting the word, right? That's kind of just like a byproduct. What we actually care about is getting this learning this projection. The whole point of this model, and with skipgram, is to learn a projection from these one hot encoded vectors into some very much more rich vector space, where all of the words are all the words that should be related are related to each other, and all the words that aren't related are not related to each other. Okay, so I hope that makes sense.
I have a question.
Yeah, what's up?
Does CBOW and skipgram have dynamic input and output, respectively, vector sizes? Or do you need multiple models to account for sentences of different sizes?
Yeah, so well, I actually don't know the answer to that. Maybe if Ben or Justin knows, they can answer. Because I was actually thinking about that as I was explaining these slides. I was thinking like, well, if if you have like a sentence that has like kind of fewer words. So I think RNNs are generally the way we get around this. And we're about to kind of discuss RNNs. So you'll kind of see why with RNNs it's not as important to have a static input size. But I think Ben unmuted, so maybe.
Oh no, I was just about to say that I don't have the answer either. But
Yeah, that's a good question. I'll like look that up actually, because I was actually thinking the same thing. These are new slides, so we just made them. So, good question. Yeah. So that's kind of skipgram and CBOW, right? So I hope you guys kind of understand the point of those two. And now let's kind of look at this slide. So yeah, so let's remember that the idea was to generate those vector encodings, right? So we can capture the relationships between similar words. Okay. So this is a kind of canonical example when we were discussing word embeddings. So we look at the three words king, man, and woman. Now remember, these are all vectors, right? So when we write king, man, woman, we're referring to like so we're assuming like, okay, you did like word to vec, you generated word embeddings to them. Like we're assuming like you have all the word embeddings now. So you have a model such that all of the similar words are close to each other in the vector space, and all the not similar words are not close to each other. So we're assuming we have that. And then if you were to take the vector for king, subtract it from the vector for man, and then add the vector for woman, what do you think? What do you intuitively think the vector that you get should closely resemble? What word should it closely resemble? Just based on your guys' own intuition. Yeah. So you guys both got it in the chat. So queen, right? So if you have king, so king is like someone in like a strong position of power, and they're also a man. So if you subtract the man part out of that, it's like, okay, someone in a strong position of power, and then you add the woman term to that. Now you're left with someone in a strong position of power who is a woman, which is queen, right? So yeah, varied in, and it's really cool, right? I think this is extremely fascinating that you can kind of generate this vector space that captures the relationship between words in a way that is actually similar to the way we think about words, right? So I think this is a very assuring kind of example of kind of, yeah, so this word embedding system actually works, and you can kind of really see that it captures the relationships between these words. So yeah, so this slide is kind of just what we just discussed. This is kind of the wrap up review slide, right? So yeah, your guys' intuition was correct. So it would be like a queen, right? So this example is kind of showing you guys how it's really important how before we kind of do some training with natural language processing, we need to make sure we have rich relationships between the words in the data set that we're working with, okay? Because if you just do the one hot encoded vectors, because you're not encoding the relationship between those words, if you were to do something like king minus man plus woman, you wouldn't get queen, right? Just obviously you wouldn't get queen, right? Because if you subtract something that has a 1 somewhere and zeros everywhere else from something else that has 1 0 zeros everywhere else, and you add something else, you're obviously not going to get necessarily going to get the value that corresponds to queen, right? Because queen could be any of the values in that vector. So I hope this makes sense. So Darren asks, I'm still confused on how word embeddings come from continuous bag of words. So the idea is that we pass in, so I'll go over this one more time. So we pass in a bunch of input words. So you have some sentence, you have some full sentence, right? So in this case, pretend like you have the sentence, the grizzly bear goes to the river to catch the fish. Like you have the entire sentence, you're not missing anything, right? And then you kind of arbitrarily take out one word out of that sentence. So in this case, let's say we take out fish, okay? And then we give the network the other words in the sentence. So everything we didn't take out, we give that to the network. And then the job of CBOW is to predict what the word that we took out was. So in this case, we took out the word fish, we took out the last word, and then we give it all the other words. And then the goal of CBOW is to predict the word fish. Now, it can only do this if it's actually generating the relationships between these words. Otherwise, it will never get anywhere, right? And this is what learning is in machine learning in general, right? It needs to learn what that prediction is. And the only way that it can learn what the prediction should accurately be is if it's able to identify the relationships between the words in the sentence. So what happens, just like how we discussed the first few weeks, you feed forward these input images, and then if it gets the answer wrong, so let's say it says potato instead of fish, then the cost value for your network is going to be very high. So then that's telling the network, oh, wow, I need to update towards the negative gradient, the same thing that we've been always discussing this whole time. I need to upgrade towards the negative gradient to kind of get my cost value to my cost function to a very low value, right? And to get the cost function to a low value, that means basically I have to be making these predictions right most of the time. And if you're making the predictions right, that means when you project the words in this hidden layer, you're projecting them in such a way that you understand the relationships between the words. Because there's no way you're going to be able to predict what the output should be if you can't generate any relationship between the words. So the idea is this word2vec model, CBOW and skipgram, they both are learning something that basically they're learning something such that the weight values that you end up with are a projection that generate rich projections of these one-hot encoded vectors to create good word embeddings.
So like, where do the actual physical values of the vectors come in? Are they the weights of the network?
Yes. So they're the weights. So you learn the weights, right? So what you do so let's say you finish training CBOW, right? You finish training it. So then what you do to get the word embeddings is you multiply the one-hot encoded vector by the weight matrix. You multiply it by that projection, and then that'll give you the word embedding for that word, for that one-hot encoded vector. So if you have a vector that's like 1, 0, 0, so we have a slide for this, right? So you have if you have like this vector, this one-hot encoded vector, and then let's say your CBOW is like well-trained. So you have this vector, and this one represents Rome, right? So you have this, and then you multiply it by the weights that we learned in CBOW, and then the resulting vector is our embedded vector for the word Rome. Does that make sense?
Yeah, thanks.
Okay, cool. Wouldn't multiplying result in a lot of zeros? No, because so I'm not gonna draw out all of it because we've kind of spent a long time kind of looking at dimensions. But think about it, right? So if the weight value, the weights in CBOW or skipgram, it's like a 2D matrix, right? So there's a bunch of rows and a bunch of columns. So each row would be the embeddings for one word, right? So if you multiply, so if we learn the embedding for this vocabulary on this slide, so that would basically mean the top row of the matrix of our learned weights would be the word embeddings for Rome, because you would multiply 1 by that top row. So then you just get that top row, and then everything else would cancel out. So you're just left with the top row, and that top row is your word. Yeah. Okay. So I hope that makes sense. It's just matrix multiplication. Yeah. So yeah, right. So the 2D the weight matrix here is like some 2D matrix, right? So each row corresponds to the embedding for one word. Okay. Because then when you multiply the one hot encoded thing, you just get that row. Okay. Cool. So that was a lot of talk on word embeddings. So now we're talking about RNN. So this might initially seem like a kind of drastic change in discussion, or maybe you're saying why are these two things related? So so Ben's going to take over here, but in the back of your guys' mind, while Ben is talking about RNNs here, try to think about why we kind of discussed word embeddings with RNNs. Think about why these two things come together well in terms of solving a certain type of problem, right? So yeah, go ahead.
Yeah,
Ben.
we might actually get to it very quickly.
Yeah.
I might blur out the answer. I'm sorry if you guys don't want to be spoiled, but
so you can go ahead and take over the sharing if you want, Ben.
yeah, right here. So should be sharing on my screen now. All right. Actually, I wanted to go back really quick, but the biggest takeaway from the word embedding slides that I think are important are, let me go back to it, is really these last two slides, the results. Like you might think, I know we said like, we talked a little bit about efficiency. We wanted to have a efficient encoding, but you might think, oh, can't we just use like UTF-8 or ASCII as an encoding for our words and pass it into the network and have our network learn their relationships. But I think this last slide really shows how, or the power of word embeddings, in that it encodes the meaning of these words and not just the words themselves. And so you can do really interesting things like do arithmetic with the words and actually get something meaningful out of it, like king minus man plus woman equals queen. And so when you have a better encoding for these words, or an encoding that captures the meaning of the words, you can, the network that you build off of it, it's easier to, like when you're doing language translation, you don't want to just take these words and, or you don't want to just, like knowing that what letters compose a word isn't as useful as knowing the meaning of the word themselves. And that's sort of one of the reasons why we use word embeddings instead of just any regular encoding for words. But now we go to RNNs. And before we get into it, I want to talk about like why we want RNNs in the first place and why we can't do what we're about to talk about, in terms of applications for RNNs with things we've seen before, like the traditional neural networks and convolutional neural networks. So what we've done so far are look at, actually, let's ask this question to see what you guys can think of. If you look at the network on the right here, this is just like a vanilla neural network. Actually, it doesn't look like it's fully connected itself, but you have an input layer, you have one or more hidden layers, and you have like an output layer. With CNNs, we kind of mixed it up a little bit, right? We introduced convolutional layers, which sort of, they're different from fully connected layers in that there are fewer weights. Not necessarily fewer weights, but each filter only looks at a certain number of neurons, and that filter is convolved across the entire, or the previous layer. So what do you guys think is in common? Do all of these networks have in common? Convolutional networks, vanilla neural networks, even like logistic regression or linear regression. Throw out some ideas and I'll open up chat to see if I can see it. Or you can unmute, that's even better.
Yeah, and I think the answer we're looking for is kind of like this answer. So like if you think what you're gonna say is too obvious, like just say it anyway, because like the answer is like sort of in plain sight for a lot of this.
Right, we got one answer. Answer is everything moves in one direction from input to output, and that's exactly right. Everything we've seen so far are feed-forward networks. By feed-forward, it's in the name. The input kind of feeds forward and goes in a single direction to the output. Another feature is that the input is non-sequential. What that means is it doesn't really matter what order the inputs are, or each of these features, each of these blue dots are kind of put into the network, right? They're kind of put all into the network in parallel. The same thing happens with convolutional neural networks. Even though we have that convolution operation where we kind of look at the filter move across the network, when it's actually like practically implemented, all of that's kind of done in parallel as a single multiplication operation. So the input, the order of the input doesn't really matter in that sense. And where's my cursor? I lost it. Here it is. Okay. And also another thing is that the data is static and the input space is independent. This is partially true because when we were looking at logistic regression or just regular or like vanilla neural networks, some problems the data is pretty independent, right? Like you have, if you're trying to predict, for example, the housing prices, you might have information like the zip code or the square footage or the number of windows, and these variables are independent. Or maybe some of them are partially dependent, like the number of windows is possibly dependent on like the floor size. Like if you have a larger floor size, then you probably have more windows. But they don't really have a relationship with each other in that sense. With convolutional neural networks, there is a bit of a relationship. There's a spatial relationship between each of these inputs, right? So this input is related to this input in that they're spatially close to each other. So it matters if we rearrange these input nodes or these elements. Like if you just scramble a picture, it's not the same thing as a picture with the pixels in a different order. And oh yeah, that's are they actually fixed? Mm-hmm.
1 second, I got some error message from the recording. I'm just going to stop it and start it right away.
Mm-hmm.
Okay. Yeah, and one thing, so another thing that I want to kind of, so Ben talked about this, but I just want to kind of discuss it a bit more. So like, what's really important is that the input that you give at one time step is not dependent on the input at another time step. And when I say time step, I'm talking about, so you guys remember how like when we discussed when we were like training models and when we were like, yeah, in like the first 2 weeks, it's like, you know, you pass in like one training sample, you do the feed forward, and then you back propagate that, and then you pass in another example, and blah, blah, blah. So each example and each instance that we like feed forward is commonly referred to as like a time step. So, and what's important here is that before the data or the inputs that we passed at different time steps didn't relate to each other in any way. So for example, you can pass like an image of a 5 at one point, and then you want to predict that it's a 5, and then you want to pass an image of an 8 at another point, you want to predict what it is. Those two inputs, like they have no relationship to each other in terms of the problem space we're trying to solve, because all we're trying to solve is what the output or what is this exact handwritten digit? What is the handwritten digit at this exact time step? Now, the question that we want to kind of pose to you guys, which I think is kind of like asked on the next slide.
Or it's on this slide. It's what type of data would result in the data not being fixed? Really?
Yeah. So can you guys think of examples where like the problem space we're trying to solve, you would need more than kind of one time step in order to kind of make the prediction?
You guys can mute and ask or talk about this. We're going to stay on this slide until we can get the recording back up, I think.
Oh, are we still not recording?
I don't think so, right?
It should be going by now.
Oh, okay. Never mind.
Okay, so yeah. So we have a good answer in the chat, right? What happens next in a video? Yeah, that's a perfect answer.
Yeah.
And Ben, you can like, yeah.
Yeah,
So
this is the slide that shows how you can have multiple images that are related to each other in terms of time. And this is one way where, like Paymon said, we have a relationship between different samples. You can kind of consider it as a single sample as well. So, I mean, you can have like a convolutional neural network that just convolves through all these images in, like taken as one at once. But there's actually there's probably a better way to do it, or that's what we're gonna kind of talk about with RNNs.
Yeah, right. So imagine like how inefficient that would be. Like imagine you have like some slow motion video that's like 100 frames per, or like 1,000 frames per second, right? And then you want to make a prediction based off of that. If you were to just use a CNN, right? So you could imagine something you could maybe potentially do is concatenate all of the images at each frame and put them all next to each other, and then kind of make one giant image, and then convolve over that entire thing, and then try to make a prediction off of that. So you can imagine like that's just like not a very good idea, right? Because for one, there's like so many frames, like there's like in this case like 1,000 of them every second, right? So then it would be a very, very large kind of input that we have to pass all at once. So that doesn't really work. And you can also kind of see how that's just kind of like not very good, right? Because like the image you're passing in at that point is like not even one image, right? It's just like a bunch of images that you put next to each other. So
yeah, and another point is that if we were to do something like that, then the input size would be fixed, right? We wouldn't be able to, or like let's say we stacked all the images up together, right? So each image would be its own channel. Our convolutional layer, like our first convolutional layer, would have to have the same number of weights or the same number of layers as it did, or like the weight matrix would have to have the same number of channels as the number of channels or like number of frames that we had. And if we had like a video that was any longer or any shorter, then we'd also have to have the network would have to have the same number of matching weights.
Yeah, so this sort of addresses not like exactly the same question, but like someone was asking about like, okay, what about like fixed input sizes like in our word to vec thing? So yeah, that's like a problem in a lot of problem spaces, right? Where like, look, we need something where our input size is not necessarily fixed. So like that was one example with the sentence, right? Like sentences can be different lengths, videos can be recorded at different frame rates, and more importantly, not even if they're recorded at the same frame rate, they might have like different lengths, right? Like even if they're 1 second, one video is 1 second longer than another video, right? The number of frames is different then, right? So it's very important that we have some sort of thing, some sort of model that's not dependent on some fixed input size. So yeah.
Yeah, and that's kind of what we're talking about when we say input sequences. So again, why are sequences useful? I'm just gonna do this so we get off it. But what we want is we want to be able to have past input kind of inform our current predictions, right? In a video, you have information about, or you can look at the previous frames to kind of predict where the ball will bounce next or where the ball will be in the next frame. And so if we just look at each frame individually, we're losing a lot of useful information by not considering any of the previous frames. And there's also other forms of sequence data, including like audio, right? And then there's also text, which like if you're doing language translation, you're working with audio and or text information. Can anyone think of any other examples of like sequential data besides like audio, text, and video, which are the ones that we've kind of pointed out so far? You can kind of put it in chat or shout it out. Let's see if I can open it up again. I don't know where the chat window went.
So someone said stock market. So that, yeah, that is, so that technically is true, but like a lot of times we use like a logistic or linear regression model to deal with those kinds of problem spaces, because you're kind of trying to fit or predict some curve, right? Which is kind of what we discuss when we discuss linear and logistic regression. But you definitely can do that, yeah. Like that's like a more advanced, that's definitely a more advanced kind of strategy that you could impose when you're trying to do like stock market prediction. So that's a great, I think that's a great answer, yeah.
Games like chess.
Yeah, I think you could do that as well.
Yeah, that's actually really cool to think about. Oh, sorry. Yeah, that's really cool to think about, right? So like you don't need to do that, right? Like for chess, like you could just look at the current state of the board and like decide the next move based off of that. But if you want to get like really advanced, right, you could be like, okay, like how did I get to this point on the board? And maybe the way that I got to this point on the board can also influence the decision I'm going to make. Because for example, like maybe the moves your opponent made in the past moves up until the point that you're currently at kind of gives away sort of how your opponent tends to play, what their next move is most likely to be. That kind of information would be lost if you just kind of used, if you kind of just only looked at the current state of the board. So I think that's a really also a very unique answer. Yeah.
Yeah. So I guess to sum it up, really any kind of information that has like that's like a time series or has a relationship through time is useful when we're dealing with RNNs, or RNNs are useful for dealing with those kinds of data. Right, so I think we can move on to the concepts for RNNs. So let's first talk about the structure. Before we had a input pass through one or more hidden layers, and then we finally have an output. With RNNs, what we're going to see is that we're going to have an input concatenated with the previous hidden layer. So we're going to have a form of state. And this state is going to be how we're going to remember past information about like the previous frames we've seen in a video or the previous words in a sentence. So this past state is going to inform our predictions, and that's going to update the state and then also produce an output.
Yeah, so what a kind of simple way you can think about this is like at each step, you're not just passing the current input, you're passing the current input and also some information about what the previous like time step was. And like maybe right off the bat you're thinking like, well, this only like deals with one time step then, right? But like not necessarily, because like that the one before, that's why it's called recurrent, right? It's like a recurrence relation, because like if you think about it, if you're passing the previous hidden layer input at this time step, that's not only, that doesn't just have information about the last time step, because the time step before that you also did the same thing for the time step before that, and it goes on forever, right? So in that way, intuitively, we're kind of, this previous hidden isn't just directly giving us information for the previous layer. It also has some sort of information about the layers before that and before that.
Yeah, if it isn't clear yet, we're gonna go into it in the next slide. So don't worry about it right now.
Yeah, there's just some intuition for like how come, like how are we getting like more than one time step, and like that very high level of like what the idea of an RNN is.
Yeah, but I wanted to note that this is really different from what we've seen so far with like vanilla neural networks and convolutional neural networks. They've really been kind of stateless, right? If you pass the same input in multiple times, they're going to give you the same output. But now with RNNs, if you pass the same input multiple times, you're going to get a different output each time. So that by maintaining a form of state, we're getting RNNs. So
yeah. So sorry I keep interrupting, Ben. But
it's all right.
So yeah, so another intuitive way to think about that is, so like you might be asking like, okay, like how come we don't get the same result if we pass the same input necessarily? So what Ben said basically is like, it's not only what you're passing in, it's what you're passing in plus the context surrounding it, right? So the context surrounding it is all this stuff in the previous time steps. And so if you have the word, like, I don't really know an example right now, but
yeah, and
the
again,
idea,
don't worry about it right now.
Yeah.
We're gonna actually get into it in a couple slides. So
yeah,
I wanted to show this slide first. So that's sort of what we had in the previous slide, but kind of illustrated more out. And this is the unfolded version, but I'll show in the next slide what I mean by that. But you can kind of see here how we have the previous hidden state and the current input passed into our network to produce an output and then update the state for the next time step. So each of these indices indicates a different time step. But like in the next slide, this is how the network actually looks like. There's going to be three sets of weights, U, W, and V. And when you unfold it, by unfolded, what we mean is we're unfolding it across time, right? In RNNs, this W matrix is going to be the same for every single time step. What changes is the state in each time step. And so that's why, while the unfolded version is kind of easier to see how the predictions are made through time, the more accurate version, or you can more accurately visualize it in the left side here, where you have a single state that's continuously updated through time, and that's where the recurrence happens, that going back into itself.
Yeah, and another reason this is like accurate, which is stated at the bottom of the slide, right? Why the kind of folded version is more accurate is because this weight matrix that you're using for this previous hidden layer, they're shared weights. Just like in the CNN, how we used a shared weight matrix over our entire like input for a single feature. So this weight matrix is like shared across every time step.
Yeah, and Darren, you also asked the question about the previous hidden layer, and we'll actually get into that right in here in this slide. So the way we update the weights is that the state is equal to the previous state multiplied by W plus U multiplied by the input. And that's the current state. And then when you go to the next state, then you multiply W by that state, multiply U by the current input, and then adding that together produces the current state. You also have another matrix V that you multiply with the state to produce the output. So the W parameters sort of tell you like how do we want to transform, or how do we want to change what we've remembered. U tells you how much information, or how do we want to transform the information that we're adding to our memory. And V kind of tells you, okay, from our memory, what are we going to actually output? So some properties of RNNs, one advantage is that they can process inputs of varying sizes, right? Since the W weights are shared across every single time step, and in fact, V and W are also shared since they don't change. When you have inputs of varying sizes, where you have like X, if you go to the previous slide, we have X t minus 1, xt plus 1, and then going on to infinity. It can handle inputs that are shorter, and it will just produce a shorter output. It can also handle inputs that are longer, and it'll produce a longer output. So that's why RNNs are different from CNNs or vanilla neural networks in that they can handle varying input sizes and produce varying output sizes. Another advantage is that the model size doesn't increase with the size of the input. Again, because the weights are shared, the V, W, and U matrices are shared, even across time steps, the weights don't change. Only the state changes. And the state is also a fixed size. So the size of the model doesn't change when you change the size of the input, which would happen if you had like a CNN or a vanilla neural network.
Yeah, and something important to note about this as well, right, is that if the parameters weren't shared, then you can't have variable length data for your inputs, right? Because the whole idea is the whole reason that you can that it doesn't really matter how many time steps you have is because you're using the kind of same weight matrix every single time you do it. So you can just kind of extrapolate this as many times as you need to for however many time steps. But then suddenly, if you have a unique weight matrix for every time step, well, that doesn't really make sense, right? Even intuitively speaking, because then like if you suddenly have if you suddenly have like a longer video, for instance, that has like a few extra frames, a few extra time steps, then you don't have any learned weights for those extra time steps at the end, right? So it's kind of by design that they have shared weights. Otherwise, you can't have this variable length input.
Yeah, and using that hidden state, we can take into account information about the previous inputs as well as the current input. And again, the weights are shared across time, and so that doesn't increase the size of our model when we increase the size of our input. Some drawbacks of it is that the computation is slow. Since the input at one time step is dependent on the input of all the previous time steps, then we can't really process multiple inputs in parallel. Like if you have a video, you're going to have to push it through the network one by one frame at a time. You can't do it in parallel because they're all dependent on each other. And it's also difficult to access information from a long time ago. By long time ago, I mean like several time steps in the past. So if we go back to the previous slide, you can see how even though we're preserving some sort of memory through that state variable, we still lose information every time, right? Because we have to incorporate information from the current time step every time we pass in a new input. We have to incorporate it, and then we update it, multiply by W. We incorporate a new input, multiply by W, incorporate a new input, multiply W. So you can see how at this time step, it's going to have a lot more, the state is going to have a lot more information about the more recent time steps than any information from really, really far back in time. And so it sort of lacks long-term memory in that sense. And that's something where we're going to show how a variation of recurrent neural networks kind of addresses that.
Yeah, another reason. So that's actually, so what Ben said is like the main reason, and then another reason that I think we have a slide for this is you guys remember we discussed the vanishing gradient problem. So actually that's like on the next slide. So I think we're gonna get to it. But that's also another reason why we kind of lose the the memory as we go really far back, because our derivatives get kind of small.
Yeah, the vanishing gradient problem really only applies during training. So you're not losing information when you're doing predictions, but you do have trouble when you're training
It's
long
hard.
inputs.
Basically, so what's hard is, if you're trying to train something that has like really long sentences or something, it's kind of hard for the network to learn like how to relate the words that are really early in the sentence to, like, if you're trying to predict the last word in the sentence, it's hard for the network to kind of relate the words early in the sentence to the words kind of that the word you're trying to predict at the end, because there's so many time steps between them. So it's hard for it to learn those relationships. And there's a question in the chat, Ben, if you want to.
Oh, I see. If the RNN outputs one prediction for some input data, then is V used just once at the final state? So there's some variations on RNN. So you can have an RNN that produces like a single output, and so that in that case you would have V just used once at the final state. But you can also have RNNs that output variable length outputs too, right? So in this case, this is what this diagram kind of shows, where you have V being applied to the state every time to produce an output that kind of has the same length or a variable length. So I hope that kind of answers your question.
It depends on what you're trying to do. And like, I think an important point to note here is that we're kind of at this stage, we're kind of discussing more of the intuitive structure of the RNN model. There's like a lot of different variations on like the details of like what exactly is the output that goes, like what is that prev hidden, right, that goes to the next layer. There's a lot of variations on that. It can get a lot more complicated, and we're gonna like look at actually like a more concrete and canonical example of an RNN in a second.
Yeah, we're going to look at a variation of it that kind of addresses some of these issues or these downsides that we're talking about here, especially in terms of memory. And to give an example or a more concrete example of when you'd want as like a single input versus like a string as an output, let's say you're trying to analyze, or if you're trying to translate a sentence, then you're going to want to do something like this, where you have multiple outputs per time step. Actually, it's not exactly like this, because then you'd also want to consider the whole sentence before you do the translation. But the idea is the same in that you have an output that can vary in length as well. But if you want to do if you want to apply V at the very end at just once at the final state, then maybe that'd be more applicable for something like analyzing whether or not maybe the video, answering like a yes or no question about a video, like does this video contain X or something, or maybe maybe you want to analyze like the sentiment of a sentence, like is this a positive sentence, is this a negative sentence, and so that would be like a single output at the end versus something that you output at each time step. Right, and I think that kind of covers the drawbacks about how we can't consider any future inputs as well. Because like it only considers the inputs before that to generate the current state, and not any inputs after it.
Yeah, so imagine like you're trying to predict, like the example we looked at the beginning of the workshop, where you're trying to like predict a word in like a missing word in a sentence. Like let's say the word is in the middle of the sentence instead of the end of the sentence. So what's problematic here is that your network doesn't really see all of the words that are like at the end of the sentence, right? Because if you're just going time step, then you get to your middle, and then you're like, okay, well, I need to make a prediction now, and then and there's like many ways. I'm sure you guys can think like of many ways that you can easily combat this problem, and we're going to explore it. So yeah.
Right. So a little bit more on these drawbacks about short-term memory in particular. As the process has more steps, it has trouble maintaining the previous steps, because you can see here there's like it takes the previous input, which is this back arrow, and it takes the current input, or not, the previous state, sorry, and the current input, concatenates them together, and then passes it through tanh. So this tanh in this case is just an activation function similar to sigmoid. We're using tanh because it has a stronger gradient than sigmoid, but it doesn't really matter in this case.
It also has so it looks very similar to sigmoid, except it's like a stronger stronger gradient, like Ben said, so it's sharper derivative. And also another big thing is that instead of the range being 0 to 1, it's negative 1 to 1. And we'll explore why that's important in a few slides.
Mm-hmm. And the vanishing gradient problem is also here because when you have a sequence of inputs, right, and it's a long sequence, then when we're doing backpropagation, it's going to have to backpropagate through this sigmoid or the tanh function multiple times. And so every single time, the gradient kind of gets smaller and smaller. Yeah. And also, it doesn't learn long-range dependencies through time steps or timestamps. No, it's time steps because, again, we have this sort of bottleneck here where every time we concatenate the previous state with the current input, we do some transformation to it, and we lose some information there. We can't retain everything since the state is like a finite size. The state doesn't grow every time we add an input. The state it remains a fixed size, and so there necessarily needs to be some information lost there. And as we have more and more time steps, we lose information further back in time. So this is a diagram that kind of shows you the differences between the gradients and why we have the vanishing gradient problem. With sigmoid, we kind of push the input from real numbers, negative infinity to infinity, to 0 to 1. With tanh, we do the same thing, except it's negative 1 to 1. With ReLU, it's we're not pushing it to between 0, or we're not pushing it between like a fixed or like a finite bound. Instead, everything below 0 goes to 0, and everything above 0 just remains the same. So it's just the identity function above 0. Here we have this bottom graph is the gradient for each of these functions. Sigmoid, or actually it's only for tanh. Sorry. With tanh, you can see that the gradient has a maximum at 0, and it's 1, and it kind of tapers off as it goes to each end. So when it tapers off like this, the vanishing gradient happens when, like, let's say the output of the activation function is something pretty high, like maybe 100. When it's 100, the gradient is actually way over here, and it's nearly flat, so it's close to 0. So when you do the weight updates, it's going to be pretty small. And when you backpropagate it further, this effect just compounds itself, and you have a vanishing gradient.
Yeah, and you can see that. So that's also why those equations. So these are the equations from workshop 2, if you guys recall, right? So like that. So like you take the derivative of your activation function, right, and you pass in your weighted input, right? So that you can clearly see why it would go to like 0 after a while, right? Because like the first step, if you're multiplying everything by a value that's really close to 0, and then you go back another layer, and then you multiply really small values that are really close to 0 because you just multiplied it by something that's close to 0, and then you do that again, you keep doing it, and a lot of times you have problems with underflowing and whatnot, and your gradients just become 0, and then you end up not updating anything.
Yeah. And with sigmoid, you're going to probably see something similar to this, except it's actually a smaller slope, or it's about lower overall. With ReLU, it's going to be like just 0 below 0, and then constant 1 above 0. So that's why it has also a stronger gradient. So now Paymon is going to take you through LSTMs, and this sort of addresses the problems that I kind of highlighted earlier with RNNs, particularly with memory.
Yeah, so I'm going to share my screen again. Wait, so why is sigmoid used then? So there's a few reasons why. Let me share my screen first, and I'll answer that.
Yeah, it will actually come up in a couple slides why sigmoid is used sometimes.
So there's a lot of reasons why sigmoid's used. One, it's usually like when you're first learning it, it's like simple. It gives like a good example of like what a lot of what the idea behind a lot of machine learning is when we're doing these things. Another thing is that, like, if you look at it as opposed to, you guys can see my screen, right?
Yeah, you got it.
Okay, so if you look at it as opposed to ReLU, right? So like Ben mentioned earlier, so ReLU is has an unbounded upward range, right? So the values are not kind of kept in check when you're feeding forward. So you can't. There's also another problem called the exploding gradient, which is or a problem of like your values explode to very large quantities. And what happens with ReLU a lot of the time is that because your value is unbounded, um, the range is unbounded, then like you're not really maintaining a certain normalized range of where your activations stand. So if you guys remember, the theme that we've been talking about is when you're doing the feeding forward process, it's important that your activations values that you're feeding forward are kind of maintained in some sort of comfortable range that we kind of are aware of. So what happens with ReLU is obviously this is unbounded, but with sigmoid and 10H, like it is bounded. So that's one plus. What commonly happens though is people just end up using ReLU, and then on top of ReLU, they use batch normalization. So you guys saw batch normalization in AlexNet a few weeks ago, and I think someone asked like, oh, what is this? So like the point of that is that because ReLU doesn't like bound the output of your activations, we use some like separate method that kind of does that. But sigmoid's nice because like it kind of does both of these things like decently well, but it doesn't do either of them like super well. So it's just like more simple when you're explaining things the first time. And there's also like a lot of like actual reasons why people use sigmoid. So yeah.
Yeah,
So
we'll see it in a couple slides.
Yeah, we'll see it. So LSTMs. So what are LSTMs? So LSTM stands for long short-term memory. So as the name suggests, the big kind of idea of LSTMs is to prevent that kind of loss of memory that happens over a large quantity of time steps. So LSTMs are just another type of RNN. They are a variation on RNN, right? So RNNs are kind of just this overarching like concept or like subcategory of neural network models, and LSTM is just like an even more kind of specialized RNN. Okay. So yeah, as the slide says, solves problem of long-term memory, and this is well, as we speak, actually, like there is a lot of research being done in this area. There's new things that are being developed, but for a couple of years, LSTMs were definitely the most commonly used RNN kind of idea or model. And we're gonna, if you take Advanced Plus Plus, we'll explore like some completely different ways of approaching problems that are in a maybe similar problem space as RNNs, but are kind of solved like without even using recurrence. And that kind of addresses a lot of problems like an inability to like parallelize things, as Ben mentioned and whatnot. But that's not important right now. We're getting ahead of ourselves. So let's stick to LSTMs. So this is gonna look like a lot, and it is a lot. I'm just showing you guys the inside of all of it first, and then we're gonna go through like each of these like little arrows and explain every step of it. We're gonna like dissect all of this information. It's gonna make sense by the end. Okay, but just at a high level, when we're looking at this one, just some things to keep in mind. So the circles represent point-wise operations. So point-wise means element-wise. So like this is element-wise multiplication. This is just matrix addition, just like anything. So these are all applied element-wise against the matrix. So that's what these represent. The convergence, another thing, the convergence of two different arrows into one arrow means that we're concatenating the result. So that means kind of if you have like you just kind of take this matrix right here, and then you kind of stick this matrix right next to it. Now you have one bigger matrix. So we're just that means we're concatenating the output. And then when we split it, it just means the same value is just being copied into two different locations. So that is just some kind of high level notational things, just so we all make sure we're understanding it. So if we just look at this, each of these as kind of a black box for a second. So this is kind of like an unwrapped RNN, right? Like how we talked about before. This model is kind of showing you it unwrapped. Kind of like this one on the left is like one time step. This one is the current time step, and this would be like the next time step. So we just show it unwrapped, so it's kind of more clear what's going on. But if you got like remember, like in reality, it's kind of like all one wrapped up thing, because you can think of it as it being kind of like a sequential, like this goes to this, that goes to this, except all of the weights here are the same. They're still shared. So like it's in actuality, it's all kind of just like one wrapped up thing, right? Okay, so let's kind of break down each of these steps. Okay, so there's a bunch of different things that this LSTM kind of does. and we can kind of like split these up into different categories to kind of make it more digestible. So the first thing we do is the forget stage. So we're going to explore this in detail first. So like Ben mentioned, a big problem that the kind of normal RNN has, right, is that, well, the size of our kind of state is fixed, right? So at each time step when we implement or when we inject new information into the flow of things, we have to kind of eject some information. And the normal RNN kind of just does this naively. There's kind of no regulation as to what stays, what goes. It's just that generally speaking, the information at the previous time step is going to kind of override a lot of the information from earlier. And obviously that's, as we discussed, kind of the reason why it's hard to have long-term memory, because this stuff gets flushed out. So what this stage does very well is it kind of learns a process for choosing, okay, what information is actually like really important from this time step that I should keep here, and what information should I throw out to make room for the new information, instead of just naively throwing stuff out. So this is a big reason why LSTMs are a lot more capable of kind of maintaining memory for more time steps, is because it kind of has a more conscious process of what stays and what gets to go. So that's the forget stage. The next stage, so the forget stage is basically throwing out all the other, kind of making room for the new information at this time step, and throwing out some of the old stuff that is not important. So we do that. Then after that, we do the store step. So the store step is kind of like the same idea as like what all neural networks that we've been talking about so far do, right? We compute what is the actual information that we care about. We extract high level features from the information at this time step. Just like the CNN, the whole point of the CNN is we're extracting each convolutional layer's objective is to extract more and more kind of dense information and pack it into some space. So that's what the store state is doing here. So for our time step, we're trying to kind of filter out all the useless information and kind of generate some rich information that we can use to make a prediction. So we do that. So we compute these two values. Next thing we do is update this thing called the cell state. I thought we had a slide on the cell state. Okay, we should have a slide for that. Oh, it's on the next slide. Okay, so we update this. So yeah, I'll explain what the cell state is in a second. But basically, we compute all these values. So we compute what we're going to forget. We compute the new things we're going to store. And then we actually apply the update to our network. And then after that, we compute the actual output. Okay, so let's kind of explore these pieces of the LSTM. So this is the cell state. This is this guy right here, the cell state. So the way I like to think of the cell state is it's kind of the master kind of brain and kind of the master of what's storing all of the information in the LSTM. It's kind of it holds kind of the memory of the LSTM, and it's kind of what differentiates the LSTM from like other neural network models. So I like to think of the cell state as a conveyor belt, kind of, that goes from time step to time step to and then at each time step we apply these operations to the cell state, right? So we apply some element-wise multiplication operation here, and then we apply some other additive operation here. So if you look at it closely, kind of all the things we're kind of like updating at each time step all kind of culminate into the cell state. So the cell state's kind of like the master, like main, like conveyor belt of information flow throughout the LSTM. Okay, so let's kind of then explore deeper at kind of what manipulations we're making to the cell state at these two point-wise operation points here. So yeah, well, I should have gone to the slide earlier, but so yeah, you can think of it as the conveyor belt. So you update it. So we call these things gates. So these update points that I'm talking about, they're called gates. So at each time step, you update the gates on the cell in order to kind of keep the cell fresh and up to date with relevant information. Okay. So this slide is just talking about the stuff we just discussed. So yeah. So now let's actually think about what we're doing to update the cell state at each point. Okay. So yeah, so this is the formula that we're using to kind of compute the things that we're going to forget about. Okay, So intuitively, before I get into the math too much, the idea is you pass through here, you pass through this sigmoid operation here. And then ultimately what you're supposed to get at the end of this arrow before you actually multiply this matrix into the cell is kind of some heat map of what values in this cell state am I going to kill. So basically, which ones am I going to get rid of and shoot down to 0? And then which ones am I going to keep? So it's going to be a heat map of values between 0 and 1. So this is why we use sigmoid here. Okay. So it's going to be some heat map of values between 0 and 1 that is going to have the same dimensionality as the cell state. And then we hit the cell state with this heat map. So basically all of the corresponding things, all the corresponding values that have a value close to 1 in this kind of matrix right here, all of those values in the cell are going to be preserved. And then all the things that are 0 are just going to be multiplied down to 0, right? So yeah, so I hope that's kind of clear of how this kind of filters out old information that's not relevant. So okay, so before anyone like gets confused here, so I'm not talking about, don't worry about exactly how it determines what to forget yet. Okay, I don't want you guys to worry about that yet. Just I want you guys to make sure you understand, like, okay, there's some heat map matrix here where each element is a value between 0 and 1, and then we hit the cell state with that heat map matrix. All the things that, so all the zeros are going to be the things that we kind of forget, and all the things that are ones are going to be things we keep. Now, when I say 0 and 1, remember, they're not exactly 0 and exactly 1. They're in a range. They're in a spectrum between the values 0 and 1. Okay, so I'm going to stop for a second because that may have been confusing. So I'm going to stop for questions for a second. And also, if that did make sense, can you guys say yes? And if that didn't make sense, can you say no? In the chat. Sort of. Okay.
Yeah, another way I like to think about it is that we're taking the hidden state and the current input, and we're using that to determine like how much do we want to forget from the previous one. Like it filters out any information that it doesn't want to keep at this point.
Yeah, so that's yeah, I'm about to get to that. So that's kind of how we determine what we're going to forget and how we're going to keep. I just want to make sure it's like the kind of math aspect is clear of how we kind of clean out the cell state at each time step. Is it basically everything that matches with the heat map dies, going with the analogy? Yeah, okay, right. So imagine, okay, for next time, I guess next time we teach this, it would be good to have a diagram of this. But imagine you have I'm going to pull out like Notepad or something, or Paint, sorry. Okay, so like, let's say you have you guys can see Paint, right? So like, let's just say it's so this is our cell state, okay? Like this matrix is our cell state. Okay, so let's say like the cell state has like values 0.5 and like 0.8, and then here's like 0.1. Okay, so this is like this is our cell state. This one, cell. Okay, so this holds like the memory, right? So this is like the conveyor belt, like here. So that's what that matrix is. And then the thing that's coming into it is going to be some other matrix that's also 2 by 2. That's going to have the same dimensions, and it's going to be a heat map of values between 0 and 1. So let's say this value is like 0.01. This one's like 0.9. This one's also like 0.8. This one's like just 0. Okay. So then what you do at this step right here is you do element-wise multiplication. So this value multiplies with this value, and then you do that for all of them. And then you get another 2 by 2 matrix out at the end. So basically, like if this value is close to 0, what that's saying is, okay, my network has determined the information stored at this element is no longer very relevant. So I'm going to kind of bottom that out or dilute it or get rid of it. And then we're saying, okay, this one has a value of 0.9. So the corresponding how much should I forget value for this element is 0.9. So that's saying like, okay, this information is still really pertinent. Like we still need to keep this. So then it's going to like mostly stay intact, because when we multiply it by 0.9, it's not going to decrease by much. So did that kind of help at all? Or can I also get more yes or no's in the chat if that kind of helped at all? Okay, cool. Yeah, awesome. Yeah, I guess next time we'll make slides for that. But so that's what we do there. Okay, so it kind of zeroes out the values that are we no longer care about. Now, what Ben was talking about earlier is like, well, like how do we determine like what stays, what goes, right? So, yeah. So remember, just like any neural network model that we've looked at so far, there's a bunch of learnable parameters here that the model has to learn on its own. It has a bunch of weights, right, that it has to learn, and those weights are kind of helpful in determining what's important based off of what it's seen in the past. In our training phase, it's helpful for determining, okay, like how are we going to determine what stays and what goes. But right now we're not looking at the training part of it. We're just looking at like, okay, how do we actually do this computation when we're feeding forward? So assume we already have like a good weight value here. So what happens, like Ben was saying, so you concatenate the input for this current time step. So like if we're trying to keep it applicable, like this would be like this would be like a certain frame of an image at some like, so one certain frame at one time step, and then you take the output from the previous not layer, time step. You concatenate those two things together. So that's what this operation is saying. So h minus 1 comma xt. So this is saying you concatenate them. And then it's exactly like we've seen before at that point then, right? So this is the normal like wx plus b times the activation that you guys have seen the entire time, right? So you concatenate the two, you multiply it by that weight value. So this is the input, you multiply it by the weight, and then you add your bias. And then you pass it through the sigmoid. For the formula, is the bias vector still a column vector? Isn't it being added to which is at least 2 columns? Yeah. I think you're right. It's not necessarily a column vector. I wouldn't worry. Ben, do you want to answer that?
Yeah. So C is more like a vector. You cannot. I mean, the dimensions don't matter because it's just you can just consider it a vector. So W times the concatenated matrix of H and X will give you a column vector.
Yeah, that's true. Because when you multiply, when you multiply it out, you're still going to end up with a column vector at the end, even though you concatenate these two values. So yeah, it's still going to be a column vector for that reason.
Yeah, okay. Like you don't have to concatenate it like this way. You can concatenate it like vertically as well.
Yeah, you can. Yeah, these are all like implementation details, right? So like we spent a lot of time in workshop 2 kind of discussing these very low level like arguments about dimensionality. At this point, it's just like, yeah, like I guess so Ben's right. Like when you multiply, it's gonna end up being a column, I'm pretty sure. So it's still a column vector, but I wouldn't worry too much about that. Yeah, concatenation vertically, that makes sense. Yeah, there you go. I like that though. I like that you guys are still like trying to keep all the dimensions like clear in your heads. That's really good. So yeah, that is the forget gate. Okay, so we spent a lot of time on that. So this WF, right? This is a specific set of weights that is learned explicitly for this little area, this little yellow box, right? So this operation right here is handled like right here in this box. Okay, so that's a set of weights that's learned just for learning how we should forget things. Okay, so that's one set of learnable parameters, and then there's a bunch of other ones here that we're about to look at, right? So yeah, so that's how we forget things, right? So we discussed the forget gate, right? So that's why as we discussed, so this is why the sigmoid's important, right? Because we want everything to be mapped from in a range of 0 to 1, because basically we either, if the value is close to 1, that's like, okay, we basically keep it. If it's 0, like we kind of diminish it. We don't really want to augment the values at this point in time, right? Intuitively, that wouldn't make sense because we're just deciding, okay, is this information still important or is it not important, right? So this slide, once again, kind of talks about the things we just spent a long time talking about. Okay, so let's look at the next state. So the store state. Okay, this one, it looks a bit more confusing, right? But at the high level, it's the same thing. So it's just the network learns a different set of weights to accomplish a different set of tasks here, right? So remember this previous, so in the forget gate, like this previous area that we were looking at, so the set of weights, like its objective, what it's trained based off of, the criteria it's trained off of is basically how well are you filtering out information that's no longer relevant, right? Now this area, so there's two other sets of weight matrices here, right? So each of these yellow squares has a weight matrix associated with it, right? So like there's a set of weights here, and there's another set of weights here, right? So we learned two sets of weights at this step. Now, as we discussed in the store state, the idea is very similar to what we've done for all the previous neural networks, right? We're just looking at the input we're given, and we're trying to figure out what information are we going to what information matters here? What are we going to actually what are we actually going to keep here, right? So this step was like, what information that we already had are we going to get rid of? And then this step that we're looking at now is like, okay, what new memory are we going to add to the cell state? Okay. So yeah, there's not much to say about this. The algebra or I guess the linear algebra coincides in the same manner as it did in the previous part. So you can perform this concatenation. You multiply by some weight vector, you add the bias. You do that here, and you do that here. So you do that once for this set of weights, the set of weights called Wi, and you do it again for the set of weights called Wc. And then you perform element-wise multiplication on the both of them. Now, the question that I'm sure some of you guys are asking is like, okay, like in this forget state, like we just had one set of weights and we just used that and that was fine. How come now we have to use two different sets of weights and like multiply them together? So when we get to questions like this, it becomes sort of, I feel like a lot of this answers to this question is mostly empirically derived. So like people, when they were designing the LSTM, they kind of experimented with a bunch of different things, what worked, what didn't work. They performed like cross-validation on different sorts of architectures and variations on this LSTM. And then ultimately, everyone dictated that, look, like doing this provides us the best results. Having one set of weights that goes to the sigmoid, and then you do the multiplication with this other set that goes to the 10H. Ultimately, it was determined that this kind of gives us the best outputs. Now, one thing I will kind of give an intuition for you guys, though, a more solid intuition for, is why is there a 10H here? Why is there not another sigmoid? So this actually does have a good answer, I think. And that's because, so as we explored previously, the 10H has a range of -1 to 1 instead of a range of 0 to 1. Okay, so when we do the element-wise multiplication here, right, we not only have positive values, we also have negative values, right? So that's cool because when we do this concatenation stage here, it gives us more flexibility in terms of how we want to update the weights, because otherwise it kind of puts a lot of burden on the forget cell. And let me kind of explain what I mean by that in more detail. So suppose that both of these were sigmoids. That means all the values here are positive, right? So yeah. So I'm just going to skip to here because we're kind of just discussing all of this at once. So that would assume that all of the values that we get here are positive, right? If these were both sigmoid. And then when you add to it, your kind of weight values in your cell are just going to go up and up and up. And then the onus is basically completely on this forget stage to kind of keep the values in check. But if we kind of use the 10H, we have a range of positive values and a range of negative values. So that's good because it sort of gives us more flexibility to kind of keep values like in a comfortable range, right? It's that same theme of, we don't want our values to kind of explode to very high values, and we also don't want them to kind of underflow to like 0. So kind of giving the network the flexibility to lower the values of the weights and also increase the values of the weights as in the cell state as it sees fit is kind of just another way that we can keep the values in check. Okay, so that kind of concludes the store state here. So yeah, so I'm gonna stop again for questions because I just talked a lot. So can I get like a yes or no on how clear that was? The math is the same idea, right? The difference is here, instead of multiplying it by the cell state, we're just doing element-wise addition. So I think the math is like basically the same. You guys, I think you're familiar with that. So can I get a yes or no if that makes sense? Okay, cool. Cool. So I got 2 yeses. I guess I'll take that. If you guys have questions, just like unmute. Yes, how determined is the architecture? Like, is this better than the rest of the ways they experimented with? Yeah, like this is like the canonical like LSTM, right? And there's very many variations on this. We actually like had a slide that we were gonna talk about like a variation on the LSTM, and then we were like, okay, that's not really. We actually like ended up deleting that because that's just like a bit like too much, and you guys kind of get the point. But the idea, so to answer that question more generally, in the field of machine learning, there's like general like structures or like qualities or like mechanisms that are used in certain architectures. So for example, so for CNNs, like any network that makes use of like convolutional layers and like feature maps, you could call that a CNN, right? And then for RNNs, like anything that makes use of this kind of recurrent idea of, okay, we not only use the current time step, but we also use some output from the previous time step. Any of those are called an RNN. So they're very broad topics. And like even when we get more detailed than we talk about LSTMs, well, LSTM is like another specialization on top of RNN where basically the new restriction that's kind of added when we talk about LSTMs is that there's usually going to be some sort of cell state. Now, the exact manner in which the cell state is updated, the order in which things are forgotten, new information is added, is not necessarily going to always be the same. In this instance, we're just giving you guys one example because, well, what I think it's most helpful when you're learning about these concepts at an abstract level to kind of have some concrete structure of like this is like how one LSTM looks. So I think like this model that you're looking at in front of you is like I think this was the LSTM that they like introduced in like the original paper where they talked about LSTMs like a few years ago. So, but there's like since been many like small like tweaks made to it and whatnot. So yeah.
LSTMs in general have been very successful
Yeah.
in being used for a lot of different applications, actually, not just like the obvious ones like translation and
Yeah, they're really strong. Very strong model.
there's
So-
also some like some of these decisions aren't all empirical. Like you can kind of come up with a reason for why is there like a separate forget and a separate input stage. Like having those two sigmoid layers and having them be separate in particular is useful because you can learn like separate parameters for forgetting information and also learning separate parameters for controlling what information gets stored in the cell state.
So some of the structure, like Ben just said, it intuitively makes sense, right? Like it makes sense that we want to separate this forget area from this like store area, and that there's very clearly in this visual you can see it, and what that basically translates to mathematically is like, well, like Ben said, you have a different set of weights for learning to forget and a different set of weights for storing. So it kind of splits up the tasks amongst the LSTM more like efficiently. And that's like a general theme in computer science, right? Like when you have some problem, the more you can break that problem down into like smaller pieces, the better off you're going to be. What I was kind of referring to is like, how come we have like two different sets of weights for this particular store stage? I don't really have an intuitive answer for you there. But yeah. But a lot of it like is intuitive, like Ben said. Okay, so that's the store state, right? So yeah, so we basically pass, yeah. So we pass 1 through sigmoid layers, and then we also pass the 10H layer, and then we concatenate those two things, or not concatenate, sorry, we multiply those two things together, and then we can and then we add that to the cell state at the end. So yeah, you guys have been looking at this for a while, so I'm assuming you guys get that at this point. Okay, now update. So yeah, update is just like apply was wait, I forget step is okay. So yeah, this is just talking about like we already talked about this. So update is just like when you like actually multiply them into the cell state. So that's all that is. It's saying like, okay, you got this value. So for this one you multiply it into the cell state. For this one you add it. So that's all the update's saying. Yeah. So apply was yeah. So the reason we split it up like forget, store, update, output is because like usually like the order in which things are implemented is like you'll compute like this heat map for the forgetting things. You'll compute like another heat map for like the storing things, and then you'll perform like these two updates after that. So that's the only reason it's like listed in this order. Yeah. Now, another reminder, right, is the trainable parameters in this LSTM are shared across the time steps, just like for the RNN, right? So like, so we have like 3 sets of weights to think about here that we've discussed so far, right? So we have this one for the forget, and then we have 2 sets of weights for the storing. So like, although these are 3 separate, completely like different numbers, different sets of weights in the model itself, remember like for each time step, like in here, like this sigmoid value in this times, or this weight value matrix in this time step is the same as this corresponding weight matrix in this time step. So it's important to remember that the values are shared, and it's also important to remember the reason why we don't care about the inputs being a fixed length or whatnot is because these are shared, because we can just infinitely extrapolate this model as many times as we need to, because it's just the same values, right? Okay, now let's just talk about the last part, which is how do we actually get the output, right? We did all this stuff to the cell state. We did all this stuff to the cell state here. We updated the cell state. We got all this cool information. Now, how are we actually going to get the output? Now, this should, so this is how we get the output. So this should intuitively make sense. So the output is a combination of the information from the cell state. So the cell state is kind of the memory that we care about. So it's kind of the context, right? The cell state's like the context of the problem. And then over here is like our current time step input. There's also like the input that came directly from the previous time step. So it's not exactly only the input from this time step, but like a general intuitive way of looking at it is like, this is like the recent. So this line here is like the recent information that you're just being presented. And then this line here is like the context. So we take basically a combination of the context and the current input that we just got. And then that's how we get the output, right? So for the current information we just got, just like all the other ones, we concatenate the previous hidden layer output with the current input. We multiply it by some fourth set of weights that we learned, right? So overall, we have 4 sets of weights, right? So this is the fourth and final set of weights. So you multiply it by another set of learned weights. You add your bias, just like you've done for all these other ones. And then all you do here is basically take the cell state. We pass it through an activation function for the same reason we pass anything through an activation function that we've been discussing for the past 4 weeks or however long it's been. Pass it through that tanh activation function, and then you perform the element-wise multiplication between the current information you just got and the context. So ultimately, I hope this gives kind of an intuitive understanding that ultimately what you get out at the end is some combination of context and the current information that you're just presented. And so this is kind of what Ben was talking about, how you might not necessarily get the same output just because you pass the same input into the network twice, right? Because this is kind of what the input that you just got along this line that I'm showing with my cursor. But we also see what's equally as important is the context here, right? So if this cell state is holding very different values, then we're going to get a very different output. So to kind of give you guys a concrete example of that, right? So if we have let's look at 2 very simple sentences, right? Like let's think about, like, let's assume the task is like determining if this is a positive or a negative sentence, right? So Ben gave that example earlier. So let's say one sentence is I like potatoes, and then the other sentence is I hate potatoes, right? So we would assume I like potatoes is a positive statement and I hate potatoes is a negative statement. So when we're kind of looking at the potato time step, right? So let's kind of trace what happens if we look through the potato time step. So the time step for the third and final word in each of those sentences. So we're passing potato here both times, right? But our cell state is going to have a very different value because in the memory here, for one of the sentences, we had something that was determined by I like. And then for the other sentences, we had something determined by I hate. So it's the cell state's job and the memory of the cell state's job to kind of differentiate between the context of those two things to hopefully, so then hopefully that way we get a positive outcome when we say I like potatoes, and a negative outcome when we say I hate potatoes. Because if we didn't have the cell state, then obviously we would get the same output for both of them when they're clearly supposed to be opposite answers, right? So yeah, that's kind of some more intuition behind that. So yeah, once again, just a quick recap of how the math works, right? So we filter the output with the sigmoid layer. That's this little yellow square here. Then we apply tan H to the cell state, which is this red guy here. And then we do the element-wise multiplication, and then that's our output. So that's this element-wise multiplication right here. So yeah, that's the math that goes into the output. And I think the intuition behind what's actually happening is more important. And I think you guys also understand that. So that was the LSTM. We have a few slides left, and I think we have a good amount of time to get through them. So Ben is, for the last time, again, he's going to share his screen and take over for the last few slides.
Yes, thank you. Right, so to finish up here, we just want to talk a little bit about the applications of RNNs. We kind of mentioned it a little bit earlier, but let's talk about them again. Some RNNs can be used in a lot of different situations, but the most common ones are like speech recognition. Again, like with audio sequences, that's like a sequential data, and it's useful to use RNNs for that situation. You can also use it for language translations, like you take an input in a sentence and you want to output the translated sentence. With video classification, and that's sort of like one of the questions, like if you have just one output, you want to apply that one output, or you just want like a single output, not just like a variable length output. You can classify like what is this a video of as well. So in each of these situations, you're taking in some kind of sequential input. With speech, it's audio. With language, it's usually text. With video, it's their images. And what they all have in common is that they're sequences of data that vary in time. But they do vary in what they output. Like with speech, you might want to output text. With language, you probably also want to output text, but a translated version. And with video, you want to output like a single class. So that's pretty much it. But we also want to acknowledge that transformers exist now, and they have kind of addressed a lot of the problems with RNNs, and it's sort of the state of the art for like machine translation or natural language processing.
Yeah, and this is very, sorry to interrupt, but this is like
Mhm.
very recent. Like I think up until like 2018, 2019, and even right now, LSTMs were like very prominently in use. But yeah, there's these things called transformers now, which use a different mechanism completely called attention, that kind of can solve similar problem spaces to the problem spaces that RNNs can solve. And they kind of solve this problem of not being able to parallelize data. So like how Ben said, like you have to compute for the RNN, you have to compute the previous time step to get to the next time step. So it solves that problem. It also addresses more of the long-term memory issues because the LSTM does a great job, but this does even better, and also vanishing gradient. So yeah.
Yeah, exactly. It's pretty much solves the same problems that LSTM solve, but kind of better. But that being said, LSTMs are still used even like pretty recently. Like 2019, I think AlphaStar used LSTMs for their model. AlphaStar, by the way. Oh yeah, go ahead.
Yeah, and this also isn't to say like recurrence is like dead. Like recurrence, like that's not what we're saying at all. Like recurrence is like a very important field of machine learning that isn't going anywhere. It's just saying like this is like another thing that exists that people are exploring for certain problem spaces. And I can't think of anything off the top of my head, but like there's definitely problem spaces that would be benefited by recurrence over like an intention-based model.
Yeah, so I mean, you can look it up yourself. You can see like arguments online. Like, are LSTMs still relevant? Yeah, kind of not. Depends. But this is the paper that talks about transformers. It's called "Attention is All You Need." I love their names. But you can read more about it, or next quarter we're doing Advanced Plus, and we actually have a workshop about transformers where we talk about it and explain it. but we don't have time for this workshop. But we can go into discussion now. So we have a couple questions. Let's see, how much time do we have? Oh, it's 8 p.m. All right, maybe not, but maybe next time we can actually ask about it if we want to review some of these slides.
Yeah, I
But
think
when
we can start with a review of these 3 questions, and then like we got through everything else. The only
Yes.
other thing we wanted to say is like there's on slide 48.
Yep, yeah, sorry. But I just wanted to note before anyone leaves, please give us feedback.
Oh
Yeah,
yes,
we're
yes.
asking about for people who are watching this asynchronously, we ask you your time zone. So we know like when to host office hours or when to like make ourselves available so that, you know, we can actually talk to you in person instead
Yeah,
of
please feedback form. Thank you. Yes.
yes, and payment. You wanted to go on this slide? Yeah.
Oh yeah, just like so yeah, that the doc for this is hyperlinked for the Conda setup. So this is an overview of what Conda is. The document is like an overview of what Conda is, why it's important, and basically like how to set it up on your computer to kind of make sure you're ready for next week, where we actually start getting really hands-on with like implementing stuff. So
yeah, we're gonna go into PyTorch next week, and we kind of want it to be a more interactive session where we kind of help you and walk through these setup steps, so that when we do the 2-week project, then you guys have all the tools you need to actually get started.
Yeah, wait, like to clarify, like you should do this setup step before like you should do this stuff on this doc before next week. Like you should, because like when we do the PyTorch workshop, we want you guys to have your like notebook or environment open so you can kind of like type the things we're typing, and you can like see it happening on your machine, and then you can, because I think that's really important for when you actually want to start coding things, to actually like yourself like start writing stuff down. So yeah, please make sure if you want to learn about PyTorch to get this ready. Now, if there's like something that's not working, like we have office hours, I think on Thursday. So like, please come to that, or like ask us like those of you who are like live here right now, like just ask us like right now, or like if there's like a small thing, you can like ask us at the that you like if there's a small thing that won't take like a super long time, or you just like have a question about how something works, you can like just ask us like next week as well, as long as like you have the setup. So
Yeah, if you're having like trouble like during the week while you're setting this up, like you can ask on Discord as well. Like you don't have to come to the office hours, but that's nice because it's in person. But if you want just like help asynchronously, then Discord is always a good option. We try to reply as soon as possible. I know it's not always like instant, but I don't think we've left any questions unanswered, hopefully.
Yeah. So Justin, I think we can stop the recording now, and then if anyone has any questions about just like anything for the live audience, like you guys can ask him now.